to recap on what we did yesterday, so just a basic revision of functions, where if I give you a function and you do f of x equals 3x plus 1, if I asked you to do f of 3, anywhere you have an x, you're going to put in a 3. If I asked you to do f of minus 4, anywhere you have an x, you'd put in a minus 4. If I said get f of k, anywhere you have an x, you'd put in a k. If I said get f of h plus k, anywhere you have an x, you put in a h plus k. And it is as straightforward as that. We also looked at then, after that, just the rate at which curves and lines and functions are changing. So once we talk about the rate of change, we're talking about calculus. It's the rate at which anything is changing, is our differentiation. So specifically yesterday we looked at this formula. It's called differentiation from first principles. And where we got it from was just looking at a PowerPoint. I'm just going to get it up here so you can see it. Oh, fuck. Sorry. So we looked at farmer measurement of cow's weight increasing. We looked at how you got that. So it was the future weight minus the original weight all over the number of days. That's eventually what you figured it out to be. But that gets average weight of the cow per day. We don't want average weight of the cow per day. We want it over a much smaller period of time. Wouldn't it be great if we could get it to be pretty much 0 time, like an instantaneous rate of change? So we looked at, you know, putting it into much more maths language, and we got this was the weight of the cow now, the time now, and then the weight of the cow in the future, because it was h days later is the time now, plus h days later is your input. So it was the future weight minus the original weight all over h, as h gets smaller and smaller and smaller and smaller. And that's what we looked at in terms of the rate at which a cow's weight is changing. To do with a function, we tried to get maybe the slope. So we took maybe using our coordinate geometry, we took a point above the point at which you want the slope, a point below it. We got 2 points and we got the slope of that, which is close to this slope but not exactly the same. So we'd like to shorten the distance between the 2 points that we picked, and the shorter the distance between the 2 points that we pick, the more accurate we will be for slope. So the closer, the less of a distance between them, the more accurate we'll be, and hence this then is the one that we use to do with functions. And this is the one you could be asked about inside in the exam, to differentiate something from first principles. So if you were asked to differentiate that one from first principles, you have to go through this process, even though you already know through your coordinate geometry that if you write it as y equals mx plus c, the slope is 4. So at least now I know what I'm expecting to get. But still, I'm going to have to go through the process because the question would have said differentiate from first principles. So now, I have f of x. I need f of x plus h. So anywhere I have an x, I need to put in an x plus h. I gives me 4x plus 4h plus 2. My formula from first principles says subtract, so get the f of x plus h minus the f of x. And when you have that done, divide by h. And then get the limit as h tends to 0, but there is no h, so it doesn't matter. As h is tending to 0, there is no h to even consider that about. The answer is 4. I was expecting that, but if they asked me to do it, to differentiate from first principles, I have to go through this process. Get the f of x plus h minus the f of x all over h and get the limit as h tends to 0. If you're happy with that, maybe just try a few of those, maybe two of those, and remember it does say differentiate from first principles, so maybe take a few of the trickier ones with the minus 2x squared or something like that and try those. You could also try question 6 there, sorry, just because it will get the idea of the application of what's going on. If you look at an example here with an x squared, if you go through the process of differentiation from first principles, so you get your f of x plus h, you clean it up, subtract your f of x, you're left with this, you divide by h, and then you think, right, the limit as h is tending towards 0. If h was getting smaller and smaller and smaller and smaller, what would I be left with here? You'd be left with 2x minus 2. So there's your answer. Now what does that mean? It means that if that's the formula for the curve up the top, that's the formula for the slope of the curve, or the rate at which the curve is changing. Why do I have a variable in my formula? Well, if you think about it, if my function is an x squared, it's a u-shaped graph that has a different slope at each point. So no wonder I have a variable in my slope here, unlike the one that I just did out where I got a constant, because if I have a line, I have a constant slope, and in my case it was 4. The slope changes depending on where you're looking at, so where you are on the x-axis.